These might look like pretty pictures, but they are actually one of the most important pieces of evidence we have for the Big Bang theory. These are called Baryon Acoustic Oscillations, and they basically sound waves from the early universe that are still rippling through space, imprinted in the pattern of galaxies. They also act like cosmic fingerprints of the Big Bang, helping us measure how fast the universe is expanding and even confirming the existence of dark energy. And incredibly, we can see them in large-scale galaxy surveys like this one. Before we get into what these are and why they're so important, first let's talk about how they were discovered, because it's pretty amazing. It's not like scientists went out looking for this. They just happened to notice it when studying galaxy surveys. In the early 2000s, the Sloan Digital Sky Survey was mapping the positions of hundreds of thousands of galaxies in 3D. Then in 2005, they published something interesting. The galaxy distribution seems to have an unusual pattern at around 500 million light years. At first, they thought it was some kind of systematic error in their measurements, like maybe there was some problem with their instruments or something. But after cross-checking with other data sets, they confirmed that no, this was a real feature of the universe. It wasn't until 3 years later that researchers realized what was going on. These ripples in the galaxy distribution are actually sound waves from the Big Bang that left an imprint on the universe and have been stretched out by the expansion of the universe ever since. Let me explain. After the Big Bang, the universe was filled with a hot, dense plasma of protons and neutrons called baryonic matter, the stuff that makes up most of the mass of everyday objects. This plasma was also filled with photons, which were constantly scattering off the baryons. This meant that the photons couldn't travel very far before being absorbed and re-emitted in a random direction. So the entire universe was in a state of chaos. But over time, the universe expanded and cooled, and the baryons started to clump together into little balls. This made the plasma more transparent because there were fewer interactions between the photons and the baryons. Eventually, this allowed the photons to travel relatively freely and unimpeded through space. But by this time, there were already little variations in the density of the baryonic matter, which caused variations in the pressure. And this led to sound waves rippling through the universe. Now, these weren't like ocean waves or sound waves you might hear every day. These were sound waves on the order of millions of kilometers in size, with wavelengths larger than the size of the observable universe. These sound waves continued to ripple through the universe, compressing and rarefying the plasma until the universe became mostly transparent around 380,000 years after the Big Bang. And that's why we call this cosmic microwave background radiation, because all the photons that were around then still exist today. And we can see them if we look in the right way. At this point, the sound waves were completely unnoticeable, though, because the universe was still very young and the features were too small compared to the size of the observable universe. But the universe kept expanding, and these sound waves got bigger and bigger, stretching out with the universe until they reached millions of light years across. And that's where they are today. Those ancient sound waves have become a sort of fossil record of the universe's past. They are the oldest light we have ever detected, and they tell us a lot about the conditions in the early universe. For example, physicists can use the wavelength of these sound waves to calculate the speed of sound in the early universe. And from that, they can determine the temperature of the universe at the time. They found that the universe was around 1700 Kelvin, which matches predictions based on the Big Bang model. You might be wondering, why sound waves? Why didn't we get, say, water waves or earthquake waves? Well, that's because the properties of the early universe at the time, such as its density and pressure, only supported the propagation of sound waves. In particular, the Baryon Acoustic Oscillations were only able to exist because the universe was not made of only baryonic matter. See, back then there was also a lot of dark matter and dark energy around. Dark matter provided enough inertia to resist the expansion of the universe, and without that resistance, there wouldn't have been any sound waves. On the other hand, if there had been too much dark matter, then the universe would have collapsed in on itself before the sound waves could form. The amount of dark matter we have now is just right to make those sound waves possible. We also learned something similar about dark energy. See, dark energy makes the universe accelerate in expansion, but it wasn't around in the very early universe. If it had been, then the sound waves would have been stretched out faster and wouldn't have had time to grow to the size we observe today. But the fact that they do exist tells us that the acceleration caused by dark energy came later. And the pattern of these sound waves has also been used to measure the expansion rate of the universe. Normally, measuring how fast the universe is expanding isn't easy. We usually use distant supernovae as a kind of yardstick to gauge the size of distant galaxies. But that requires knowing the absolute brightness of the supernovae. However, the Baryon Acoustic Oscillations provide a completely independent way of measuring the expansion rate because the wavelength of the sound waves is directly related to the size of the observable universe. By measuring the wavelength, we can work out the size of the universe and therefore how fast it's expanding. And amazingly, we found that this method agrees with the measurements based on supernovae. And finally, these ancient sound waves may help solve one of cosmology's biggest mysteries, the nature of dark energy. You see, as the universe expanded, the amplitude of the Baryon acoustic oscillations decreased because they were stretched out. But it turned out that the rate of that stretching was higher than expected. Normally, you'd think that the answer to this puzzle is that our models of gravity are wrong. But there's another possibility. Maybe dark energy isn't constant, but changes over time. There's an idea called quintessence, which is a type of dark energy that changes in strength as the universe evolves. And recent studies have found that varying dark energy fits some of the observations better than a constant value. If that's true, then these ancient sound waves will get out of step with the cosmic microwave background. This will break the tight connection between the two, which will be one of the smoking guns for varying dark energy. Even though these discoveries were mostly made in the 2000s, the story isn't over. We've only discovered them in 2 dimensions. If they really are a 3D phenomenon, then we should be able to see them in galaxy surveys with more depth. One project trying to do just that is the Dark Energy Survey, which has been imaging 1/8 of the night sky every night for 5 years. After analyzing all their data, they found good evidence for the Baryon Acoustic Oscillations. They measured the 3D structure of the universe around 6 billion light years away and found that the results matched the predictions of the standard model of cosmology. The next step is to measure the speed of these sound waves, which will require even more data. One of the best ways to do this is to use what's called the power spectrum, which essentially measures how the amplitude of the sound waves varies with wavelength. Once we have that, we can fit a model to the data and get a value for the speed of sound. This will tell us the temperature of the universe when the sound waves formed, and that will put more constraints on the models of the early universe. So there's still more to learn from this unexpected discovery. And hopefully it'll reveal more secrets of the universe's history and evolution. I'm a science communicator based in London. I love talking about space and physics and all the amazing discoveries we make through scientific research. If you want to know more about the universe and how we explore it, follow along for more updates.